Hello, everyone. Thank you for joining us today. My name is Yasmina Greco. I'm with O'Reilly Media, and I will be your host for today's online conference. I will turn the program over to Julie Steele for her opening comments in just a moment, but first I'd like to go over some housekeeping things to help you get the most out of today's online conference. You'll want to open the group chat widget if you haven't already done so. This is where we can interact with each other during the event and where you can submit your questions for today's speakers. We find that our audience usually has a lot of good knowledge to share, so we encourage you to chat freely during the event. However, if you have questions for the speakers, please be sure to preface them with a capital letter Q so we know that it's for them and we can make sure they see it for Q&A. You can also open, move, and resize any of the other widgets. If you'd like to tweet from the Twitter widget today, you may need to give it permission to access your account. Our hashtag today is Strata Rx, all one word, and the Twitter widget will automatically append it to your tweets so you don't have to. If you have any problems during the event, please take a look at the Help widget. If you continue to have problems, please post it in the chat room and one of our staff will help you right away. For choppy audio or stalled visuals, please try refreshing your window. And remember, the best thing you can do for a good audio stream is to close any apps that could interfere. People always ask, so we'd like you to know we are recording today's online conference and we'll have an archive ready usually within 48 hours. And folks, at this time, it is my pleasure to turn the program over to Julie Steele, your chair for today. Hi, Julie.
Hi, thank you, Yasmina, and thank you to all our attendees for being here, as well as our speakers. Today's topic is personalized medicine, and this is a topic that's really intriguing because the promise of personalized medicine is so enticing. It holds out the promise of allowing us to target medications and other treatments, which means that patients will receive the most effective care possible in an efficient manner without delays of the kinds of trial and error that we do right now. It also means less waste in the system, which means lower costs for providers, insurers, and families, which is important because of the amount of money we're currently spending on care. We've made exciting advances toward personalized medicine in recent years with the ability to analyze individual genomes, which is quite powerful, and the cost of doing so is rapidly falling. We know that companies like 23andMe are amassing vast genomic data sets, and interesting insights are coming out of that. But there are also challenges to building data sets of personalized genomic information and other kinds of information that would allow us to deliver personalized medicine, as we well know. One of the most important challenges is building a representative sample. There was a period of time, somewhat famously, in which doctors had the wrong idea about the typical size of the thyroid gland. This is because learning autopsies were nearly always performed on poor people who couldn't afford proper burial, and many of these poor people were malnourished, which had led to swollen thyroid glands as a result. But because that appeared to be typical within the research sample that they were collecting, doctors suspected the occasional complaining wealthy person of having a so-called shrunken thyroid. And it wasn't until much later, this perception persisted for close to 100 years. So we've seen in the past the necessity of having a well-rounded sample, and that's something we still continue to struggle with. Our first speaker today, David Heckerman, will speak to us about the challenge of accounting statistically for the diversity of people in a data set. And then we'll hear from Michael Simpson about creating a comprehensive data set of phenotype data through crowdsourcing and distributed distribution models. Arijit Sengupta will tell us about the transformative potential of analytics when we build those into the day-to-day activities of every level of the organization so that they can lead to real actions from every person on staff and not just data scientists or model builders. And then finally, Ann Waldo will look at the privacy implications of personalized medicine and help us to identify some of the legal obstacles that are currently impeding research in this area. She'll also suggest some possible mechanisms of reform that would remove or reduce these obstacles. So without further ado, I'd like you to help me welcome David Heckerman, who is the Senior Director of the eScience Group at Microsoft Research, who will speak to us on discovering genetic associations in large data. David?
Well, thanks, Billy. Thanks for inviting me. I'm using an echo, so let me switch off speaker. Testing 1, 2, 3. Much better. Can you still hear me?
We can hear you.
Great. So my talk is going to be about discovering genetic associations, and in particular doing so on large data. So when it comes to personalized medicine, one of the key things we want to be able to do is to find these associations between genetic markers and traits of interest. In the case of medicine, some of the obvious traits that we're going to be interested in looking at is whether or not you're going to get a disease or the propensity for you getting a disease. We want to consider whether you're going to react badly to a drug or react favorably to a drug. And the more we look at these problems, finding associations between genetic markers and traits, the more we find that, at least for common diseases, these associations are very weak. There's usually lots of associations, or there's associations between lots of genetic markers and a given trait, but each particular association is very weak. So in order to find these associations, we need lots and lots of data. Now, fortunately, we are getting lots and lots of data because, as probably most of you know, there's an exponential decrease in the cost of sequencing the genome that's happening. So a little bit over a decade ago, it cost $100 million to sequence the first human genome, and now we're about to see whole human genome sequenced for under $1,000 a person. And in addition, right now, for under $100, you can measure easily 1 million genetic markers in an individual. So that revolution that exponential decrease in the cost of sequencing DNA is leading to this wealth of data that, at least in principle, can help us find these very weak signals. But now the issue is, how are we going to do it? So one of the common ways of looking for associations is what's called the Genome-Wide Association Study. And what you do is you collect data for as many individuals as you practically can. You collect data on individuals who have some trait of interest. For example, they might have some disease. And you collect more data on other individuals who don't have that trait. For example, they don't have the disease. And then you measure, let's say, 1 million or more genetic markers for each individual, and then you look for differences between differences in the genetic markers between the two groups of people. And the map that I show here, each one of these bars, vertical bars, is one of your chromosomes. I think they're labeled 1, 2, 3, and so forth from left to right, top to bottom. And each colored dot next to a particular position on a chromosome corresponds to some interesting findings. So some interesting association between a marker on that part of the genome and some particular trait of interest. So as you can see, there are many, many associations that have been found. And in fact, this slide is rather old, and there are many more than what's shown on this slide. And you've probably heard, driving on the radio, probably every week, some announcement of some new finding of this sort, some association between your genetics and some trait of interest. Now, just to give you an example of something that we've done in my research group, we took about 500 people from Finland that have Lou Gehrig's disease, otherwise known as ALS, and another 500 people who didn't have the disease. And we did this search for differences across the genome. And we found a few markers in a particular region that had a very strong association with whether or not you had Lou Gehrig's disease. And then Brian Traynor at NIH, it took him a couple of years, but once we knew there was a clue that there was a genetic marker that was in association with Lou Gehrig's disease, he went in and in detail looked for what was the actual genetic change that was responsible for Lou Gehrig's disease. And he found it, and we now understand that this change accounts for about a third of all familial Lou Gehrig's disease, at least in Europe. So this gives you an idea of sort of the exciting things you can do with these genome-wide association studies. Now, these studies have been going on for several years now, and all the obvious, very strong signals have been found. Maybe not all, but a good number of them. And so most of the remaining signal is weak, as I had mentioned. And so we need, again, as I mentioned, lots of data to find these signals. And various groups are collecting very large data sets. Just to give you an idea of how large they are, groups like Decode, 23andMe, and Kaiser have all collected over 100,000, a large set of genomic markers for over 100,000 people. Okay, so now when you're in this situation where you're collecting lots and lots of data, what often happens, as Julie mentioned at the beginning of this session, you get what's called confounding. So you do a rather straightforward statistical analysis, and you find a very strong association between some genetic marker and a trait of interest. And it turns out that that association is false. It looks real when you do the statistics, but it's actually not real. And what's going on is what's called confounding. Examples of confounding are you have in your data people with multiple ethnicities, or you have closely related individuals, and because of this, you get these false signals. And let me try to give you some idea of how this happens. Let's just consider a single genetic marker now, which can either be an A or a T. These are the nucleotides. And we're looking at one particular, let's say, disease. And in this figure here on the left are the people who represent people who have the disease, and on the right are people who don't have the disease, the so-called controls. So if you look at this data naively, you see, the cases, there's more A's than T's. Each circle here corresponds to a particular individual. And then if you look at the controls, you see, there's more T's than A's. So you think you found an association between this genetic marker and whether they have the disease or not. But it turns out this is a false association for the following reason. It turns out that in this data, there's actually two populations of people. You can think about them as different ethnicities. And in population 1, there's more A's than T's. And in population 2, there's more T's than A's. And it just so happens that in the cases, there's more people from population 1, and in the controls, there's more people from population 2. So that gives you a false signal. And so what we want to do is avoid this and yet use lots of data, for which this sort of confounding is almost inevitable. So how do we do that? Well, many decades ago, animal breeders had the same problem, and they figured out how to solve the problem, at least in principle. They developed a statistic model called linear mixed models. These models are great for finding these hidden confounders and getting rid of them. But there's a catch, and that is they're very computationally expensive. So for those of you that know computer science, if you're analyzing n individuals, the runtime will be O(n) cubed, and the memory use will be O(n) squared. For those of you that aren't computer scientists, just appreciate that once you get over about 5,000 individuals that you're trying to analyze, you can't do it with this algorithm. But what we've done in my group is to figure out with some basically algebraic tricks how to bring down these heavy computations to very simple computations and not sacrifice the accuracy of the result. In fact, what we were able to do was show that using the tricks that we developed, not only were you able to make the algorithm run faster, but you actually got more accurate results than you did if you used it the traditional way. And that's a very rare thing that happens in computer science. Usually when you're clever enough to think about how to speed up an algorithm, you usually introduce some sort of approximation, or you sacrifice the accuracy of the results somehow. In this case, it actually was the opposite. By running faster, we were also able to run more accurately. So we published this work in Nature Methods in 2 different publications. This is joint work with Jennifer Lisgarten and Christoph Lippert. And we are now taking this algorithm, and because we were able to speed up the analysis so much, we're now tackling problems that are very difficult, and here's an example of one. There's some data from the Wellcome Trust for 7 common diseases, including coronary artery disease, hypertension, type 1 diabetes, type 2 diabetes, and so on. They have lots of individuals in that data set. There's about 15,000 individuals. And what we were able to do is analyze, not only look for associations between single genetic markers and whether or not you have this disease or not, but we were able to look at interactions between these genetic markers, what are sometimes called SNPs, or single nucleotide polymorphisms. So if you look at the markers that were measured in this Wellcome Trust data, there's about 60 billion pairs of them. So we asked the question, for every one of these 60 billion pairs, we asked the question, is there an interaction between these SNPs and whether or not you get this disease? So because of FastLim and because we have a nice parallel computation environment at Microsoft known as Azure, we were able to do these computations in a relatively short period of time. If you were to do it on a single machine, it would take 400 years, but we did it, in a day or so. Sure enough, we found some new interesting biological interactions in this data, which unfortunately I don't have time to talk about today. So in summary, when you're looking for these associations, it's good to have a lot of data because a lot of these associations can be very weak, at least when you look at them one SNP at a time or one genetic marker at a time. But there is an algorithm that can handle this. And when you have lots of data, you have this very large possibility of confounding. And fortunately, there's an algorithm that can handle this confounding problem, namely linear mixed models. But now we've made them practical to use. And if anyone out there is interested in trying it, it's available free for academic use. Just search for FastLim and you'll find it. Thank you very much.
Thanks, David, so much. I don't know if there are any questions out there in the audience for David. If there are, please chat them to Yasmina now. But I have a couple of questions. First of all, you talked about quote-unquote strong associations to certain diseases such as Lou Gehrig's disease. And I'm wondering, how do we get from a strong genetic association to discovering an actual cause of a disease or a potential treatment? Since we know that correlation does not equal causation. So what do these strong associations actually tell us in terms of making progress towards treating a disease?
Right. They're the first step in identifying the cause. So when you measure 1 million genetic markers across the genome, the actual genome is 3 billion markers long times 2 because you have 2 chromosomes. So usually the association you find with a particular marker, sometimes called a SNP, is not the actual causal marker. But because you find an association, there's a good chance that the actual cause is nearby because as DNA gets passed from one individual to another, you go through this meiosis process, and pieces of DNA that are very close to each other tend to travel from one individual to the next together. So if you find an association, there's probably a cause nearby. And what you then do is go to the lab and start sequencing the DNA around the area that you've identified, and that's exactly what Brian Traynor did in the case of Lou Gehrig's disease. And with a lot of effort, he finally found the genetic change that was responsible for Lou Gehrig's disease after doing a bunch of additional tests to verify that.
Mm-hmm. And so now that you can do these computations so quickly, what are the limiting factors or the bottlenecks to further progress? Is it simply, genomes to sequence, or?
Yeah, I think now that we have this algorithm that is so fast and it can handle millions of individuals or data from corresponding to millions of individuals, I think the real challenge is getting a lot of data in a systematic way. Or by that I mean getting data from a lot of individuals.
Yeah. Well, thank you so much, David. And that's actually a perfect segue into our next speaker, because Michael Simpson is going to speak with us about getting data from lots of individuals through crowdsourcing. And so Michael Simpson, who is the president and CEO of TraitWise, will now talk to us about crowdsourcing, specifically phenotype data. Michael?
Thank you very much. I think I'll start by kind of giving a little history of where TraitWise came from and what we're trying to accomplish. We started with a group of scientists and actually gaming programmers going back about 5 years now, who were looking specifically at personalized medicine and how do you make sense of that deluge of genetic and chemical data, that these really large data sets that are getting cheaper and cheaper every year, following Moore's law, maybe even plus some. And the conclusion was the only way you're going to make sense of those very large data sets, including the genome, was to have a reference data beyond saying, okay, this group has a disease and this group doesn't. But there are so many various phenotypic issues, and we use phenotype very broadly to mean basically everything about the human condition that's not genetic and not chemical. So obviously, how you respond to a treatment or what color hair you have are very clearly a phenotypic presentation of your genome. But there may be other things that what colors do you like, and things that are much less obvious in terms of understanding what is a phenotype and what could impact our ability. So we took a look at the problem saying, how do you get a large amount of phenotypic data that can then be used as a reference data set to compare to the chemical and genetic? And the conclusion was the only way to capture that data is to create a crowdsourced way of accessing maybe that most complex sensor in the home, which is the human brain. And how do you get people to talk about themselves in a systematic way and make it fun and even engaging? So we took that as a process to create, in effect, a survey that would allow people to talk about themselves. And instead of going, trying to create a portal, which is what many other organizations have done, and try to drive traffic to it, we created a tool that can be used, basically by all organizations to gather phenotypic information. So we've created an engaging, a white-labeled survey tool that's embedded right on your website or on a researcher or organization, and that can be used to engage with a audience, with a population group, to start getting the information. The key thing about TraitWise is we've made it using gaming paradigms such that you get 10 times more data than other survey tools, and where it actually makes it fun, even addictive. Now, the best way to actually experience this is not through PowerPoint, so at some point after the call, I highly recommend you go to traitwise.com or app.traitwise.com and take a look at the technology. So this will give you a little bit of an idea on the slide. So as a user is answering questions, the user gets immediate feedback as they answer it in terms of a histogram and how do they compare to others. And then a new panel slides in at the top with a new question. And this goes a long ways towards creating anticipation and eliminates any kind of page navigation so people remain engaged. And this is really the critical gaming paradigms that make answering questions both fun and addictive. Another thing that we do is we start providing some of the results. How does one question correlate to another? And then we ask people to rate them in terms of their interest level. So we start various aspects of crowdsourcing so that the ones that get higher rated are more likely to be presented to people. Once again, maximizing that engagement. People want to stay on and answering questions. Another way that we do the crowdsourcing of it is ask people to pose their own questions. Right now we have well over 5,000 questions in the data set and growing every day as people say, okay, well, I've answered these 10 questions on diabetes, but I think this is really important to me, and I wonder if anyone else sees that. So they can pose that question to the population and, once again, grow the data set. Very much like Wikipedia, where is now much larger than any other encyclopedia out there because it takes advantage of the wisdom of the crowds. What is the right question? even crowdsourcing the questions itself is a critical component, not just trying to crowdsource the answers. So this is highlighting the add a question button and highlighting how people can rate each one of the panels in terms of the intracellular correlations, or whether even the question is good or bad. And once again, our algorithms bring up things that are more engaging more often. And because of this, we get very high utilization rates of the software. Now, how it actually works is the technology, the tool gets embedded right on our customers' websites. Each one can have their own survey targeted right to their audience and build this large data set that can be used to personalize medicine. But one of the most important aspects of getting the big data and getting the data sets that we need to personalize medicine is making it engaging. So we did a white paper research, and we found that by embedding a survey on the website for someone they trust already versus being a click to a third-party survey, you're 2.5 times more likely to get someone to start responding to the surveys. And ultimately, that engaged user is makes fewer errors and is much more satisfied with the experience. Once again, critical to getting people to participate. And secondly, we found that people are going to answer about 4 to 8 times more questions using the trait-wise technology, where they're getting that instant feedback and creating that sense of anticipation. And it just becomes fun and addictive. So it's not unusual for people to answer from 500 to 1,000 questions, which means that people are willing to spend hours just benchmarking themselves to others. And the average was about ranges from 40 to 50 questions per person for each time they sit down. When we look at that compared to other survey tools, they were averaging around 10. So it changes the whole paradigm in terms of it's much easier to collect the information that you need to start making broad associations. And once again, this doesn't, as we talked about before, an association does not necessarily mean causation. But we look at this type of information as kind of a hypothesis-generating machine, where you can start looking for associations and then using the scientific methodologies, go and see what it takes to find the causality. And the last key part to keeping people engaged was we asked people to rate our technology, our survey technology, versus others. And not only do you get more questions answered, but people enjoyed the experience more. And of course, I think those go hand in hand. And while this may sound like a trait-wise pitch, it's really critical as well in terms of gathering the information and the data needed to supplement the other data sources to start looking for system-wide correlations to actually make progress on personalized medicine. And this can be used for all different types. At this point, I'm actually going to skip the remainder of my slides, which are much more of a trait-wise pitch, and I won't go into that. And and feel free to ask questions about how this can be used to solve specific data problems. So thank you very much.
Thank you so much, Michael. So we do have a couple of questions for you. First of all, I'm wondering, can you tell us a little bit more about what is it about phenotypic information, which I'm sorry that we didn't explain this word before in case anyone on the line isn't familiar with it, but phenotype refers to sort of those observable physical or biochemical characteristics. So what is it about that characteristic information that might give us better or additional insight that we can't get through something like genotypical data or other measurements alone? Why is that worth collecting?
It's a little bit like trying to learn a foreign language. If you're looking at at a set of genome data, there's no way just comparing it to itself to really understand what it means. So you need to have a reference, the Rosetta Stone, of a way to say, okay, here is a set of things that we can identify easily because, what's my hair color, or do I react poorly to a drug, or do I have a specific disease, or what's my favorite color, or my personality is such. Like I said when I started this, we use phenotype very broadly to mean everything about the human condition that's not genetic or chemical. And that becomes that reference data set that you can start looking for correlations to changes or to specific characteristics within a genome or chemical data set. Does that answer the question? Or?
It does, yeah. So Doug in our audience is wondering how you avoid instilling bias in responses when you're showing how the individual relates to the crowd.
Well, two things. One, of course, you don't see the response till after you've answered. And secondly, we actually do allow people to change it, but we record every response. So we can look at the data and analyze it for various features. One is, did they consistently change their answers, and did they change it to the majority? Did they answer so fast that they couldn't possibly have read it? And by going after large data sets, then you can weed out data that is either always the first question, it always changed to the majority, or is going faster than we believe possible to be read. So there's ways to do analytics on the data itself and to basically segregate data that may be suspect, and then run various hypotheses. Does it change if you segregate some of the data? But the key thing is having all of it available, having it where you can look at it.
Do you use a controls group, or how do you get those benchmarks to figure out, for example, if someone is answering too quickly?
Yeah, exactly. So we have massive amounts of data on each question, and you can look at a distribution of of the answer time, and you can decide, okay, I want to throw out the outside of 2 standard deviations or something like that. So you can make various statistical analyses, or you can even go through and do a control time for a set that there's various different ways that our customers go and approach that problem.
Yeah. And then finally, Anne is wondering if your survey takers are identifiable.
It's 2 different ways that we can do it. You can do it anonymous, and so completely not, or you can have people logged in. And once again, one of the key things about what we do is we embed it onto our customer's website. So we're not looking for, like statistical populations, like if you're doing polling for, what the political results are. We're targeting a specific audience and trying to engage them. So a lot of them, most of our customers do know who the customer is, who the user is, I should say, and because they're logged into the site and they're answering, and we provide the key. Now, TradeWise doesn't know who it is. It's anonymous to us, but our customer knows who it is because they're providing a unique identifier. There are cases where anonymity is important, and that can be done too, and can be clearly stated, at the onset of the survey.
Well, thank you so much, Michael. Our next speaker, Arijit Sengupta, holds many titles, and one of which is the CEO of BeyondCore. He's going to talk with us now about something that he calls advanced analytics for all, which is basically the process of enabling everyone at every level of a business to act on analytics intelligence. And specifically, he'll speak to us about a case study looking at the length of stay patterns at a particular hospital. So, Arijit?
Thank you so much. I hope you can hear me. I'm going to skip a couple of slides, but basically, here's a quick introduction for my background. Easiest way to think of me is a recovering geek, if you will, but you can't take a geek out of a person after all. And the team is basically a team of very interesting math and science experts out of Stanford, MIT, and to some extent Harvard, multiple math Olympiad gold medals, etc. And we have gotten several awards. Let's skip through all this and get to the meat of the real presentation. We believe access to analytics is broken because what is important is how do we get everyone who impacts the business outcome for whatever we are trying to do, how do we get analytics to them? And the issue becomes that today senior executives and to some extent middle management have access to analytics, but the majority of the organization actually doesn't. And from our perspective, it is actually more important to have the admitting nurse have access to analytics than it is perhaps to have the CIO of the organization have direct access to analytics, because that admitting nurse can have a bigger impact in some cases. The second issue is everybody is talking about big data and advanced analytics, and what they forget is big data does not equal manual analysis, right? So for example, people are trying to do a lot of effort around looking at what more data can I add into my analysis. But as they start looking at different variables, for example, one of the hospitals we're working with, they wanted to analyze things down to the level of what hospital bed was a patient in and what X-ray machine took the X-ray of the patient, because their concern was, could we track down an infection, for example, to a specific bed in the hospital? And if there's a lot of infections happening in that bed, maybe we find out that there is a vent somewhere near there which is causing the increase in risk of hospital-acquired infections, right? So you're getting into a lot of variables. The problem is the moment we start looking at more and more variables, and we want to look at second, third, fourth order variables, combinations, such as if you're looking at a medication, forget about personalized medication. At the very least, you would want to know what medication is better for me given my gender, given my race, given my smoking history, perhaps my BMI, right? Even at that point, you're at a four-variable, fourth-order analysis, right? And the amount of computational complexity goes up exponentially. So if you're looking at 100 variables and you want to look at fourth order, you would have to write 94 million calculations. That's clearly not possible for a human analyst to go look at all of that. And of course, you must have read this McKinsey report that talks about the unmet demand just in the U.S. for 140,000 to 190,000 analytical talent. But what we find even more fascinating is the need for a really large number of business users to become trained in statistics. Fundamentally, I don't think this is a problem we can solve with training or through outsourcing. Some people are trying to outsource this. In fact, what I found really funny was this year we got the Gartner Cool Vendor in Business Process Services, and another company that got the exact same award is Mu Sigma, whose premise seems to be, well, I have analysts for $40 in India. So I don't think that model is long-term going to scale because there's just too much data. You're not going to outsource your way out of the problem. So what we believe is there's a need for a new approach to analytics, which we call advanced analytics for all. And I'm going to go through the principles of advanced analytics for all, what we are trying to do, and what we are encouraging other organizations to do, and then go into a case study. By the way, on a separate hat that I wear, I chair the Big Data and Advanced Analytics Special Interest Group at the Service Research and Innovation Institute, which was started by IBM, HP, several others. And that's one of the efforts we are doing in that group is how do we help analytics companies understand how to truly impact outcomes, which is going to be through simplicity and making the technology more pervasive, more easy to use. It's not just going to come from computational complexity, if you will. So one of the things that we started out when we first looked at the Advanced Analytics for All premise, I basically went to my engineers and I said, you know what, SAS code is, and this is an example of SAS code, it's just too difficult to do. We can't require people to have any statistics or computer science knowledge to have to do analysis. And they fought with me a little bit, but then they got the point and they went in and built a product. The problem was the few people who can actually do something like that, where they can enable an analytics platform which does not require computer science and statistics skills, well, they are such experts in statistics that every aspect of statistics is easy for them, right? So it almost became a self-defeating goal from my side to tell the best statistics experts, make the product not require statistics skills. So then we went in and said, well, you know what? It can't require a keyboard. Everything a business user has to do to run an analysis has to involve nothing but selecting. So that's something a business user can do. And if we can get a solution where a business user just comes in and says, hey, here is my business outcome. So in the case of the example I'm going to show you, the business user comes and says, I want to look at excess length of stay. So how long did the patient stay in the hospital, less the amount the Center for Medicare and Medicaid suggests is the appropriate length of stay for that diagnosis, right? I want to look at excess length of stay. I'm not going to tell you anything else. Go look at every other variable combination, figure out how that affects my length of stay. That's something a business user can do because all they're doing is going in and selecting something. Another interesting benefit of this approach is organizations are very concerned about the quality of the analytical code that's sometimes written and the maintainability of that. So, for example, Deloitte's economic consulting group used to have two PhDs create the same SAS code because they were afraid that one PhD might make a mistake, so they would use up two PhDs to run the code just to make sure there were no mistakes in it, right? Whereas if you have a solution which is focused on visual approaches, it's very easy for another analyst to come in and look at an analysis setup and say, oh, I see what variables have been selected. I see what options have been selected. Okay, I get this, right? So it becomes organizational knowledge, not individual knowledge. But that's on the analyst side. The other side is the consumer, the person who's going to look at the report. The problem is human beings do not communicate in terms of mathematics. Think back to all the conversations you have had with your friends, even analysts. Think back to the conversations you have had with your business users. The conversations always came around to stories. Stories and examples is exactly how human beings tend to communicate with each other. So let's say I come in and tell you the diagnosis code, the name of the hospital, and maybe physician is highly correlated to excess length of stay. And I tell you that the R-square is 75% for these three variables as opposed to R-square being 55% for another set of three variables. The reality is some experts may get what we're talking about, but to the vast majority of people in the organization, I just spoke Greek, right? It doesn't mean anything to them. But if you go to that exact same people and you say, look, we looked at a procedure. In this case, the example on the right-hand side is a procedure called tracheostomy, where you cut a hole in the throat. And the software found that this hospital in Detroit is taking 14 days longer, is keeping patients 14 days longer than this other hospital in Chicago. Now, that is actionable. Because firstly, you immediately understand how important this is. 14 days difference in length of stay is a huge difference. At the same time, tracheostomy is something that is a very specialized treatment. It can be that a person had an infection and thus they had to do a tracheostomy and there are complications involved in it. So it may or may not mean that there is a fundamental problem. But now I know where to look. If I think of all the diagnosis codes I could have looked at, all the treatments I could have looked at, now I know, okay, of all the things I could have looked at, let me go take a look at tracheostomy. Also, when people are talking to each other, when they collaborate, it's much easier for them to say, hey, I want to see what's happening with Chicago for tracheostomy than to say, I want to look at how the variable hospital is getting affected by the treatment code, for example. Next is collaboration. Now, in the first of the advanced analytics slides, I was talking about how you want to have computers run the analysis. And that, of course, runs hypothesis-free. You're basically not going in and saying, hey, I'm going to go look to see how diagnosis affects outcome. You're just going in and saying, show me what's interesting. But human intuition can never be taken away. So the example of the tracheostomy one I was talking about, it might very well be the case that when you pull the files, you find this is not a problem at all. Detroit actually had a case mix that makes it perfectly valid for that to have happened. So you need human intuition, but how do you do that? You can't do that through in-person meetings. So if you want advanced analytics for all, what you need to do is social collaboration. So people need to be able to come in and look at a graph and comment on it and see and ask a question to their colleagues. And if I've asked a question to my colleague and my colleague comes to that same site and clicks on my question, they should be able to see exactly what graph under what settings was I looking at when I asked that question. Is there a part of the graph that I was interested in? And that's how we need to overlay human intuition on top of the automated analysis. So you don't throw away human intuition, but instead of putting it at the beginning of the analysis where you force humans to find hypotheses and they may not think of the right hypotheses, you're putting the human intuition in the back of the analysis where interesting statistically sound patterns have been found, and now the humans come in and say, why is this happening? What is happening? Add that richness of human intuition on top of that. The next thing, and this is crucial from my perspective, a lot of analysis companies are basically taking the position of, hey, I encrypted the data, I provided you a password, now I'm done. I'm going to put a legal disclaimer, and that's the end of my thinking around privacy. Now, this is a fairly dangerous approach because it's almost like giving someone a loaded gun and saying, I didn't even put a safety into that gun, but if you shoot yourself, it's your own fault, right? And this is going to become one of the big problems with big data analytics because people are already getting a little nervous about this Orwellian world that could come about if we have this kind of lack of consideration for privacy. Now, one information that will probably scare you a little bit is Harvard, this lady who heads up Harvard's data privacy lab did a research where she showed 87% of the people in the United States can be uniquely identified by just zip code, date of birth, and gender. Just zip code, date of birth, and gender. You don't need anything else. Now, that's a very scary thought because most of us don't think of that as private information, but this becomes a problem because people today are doing search-based attacks. And if most zip codes have so few people that you can run a search-based attack and identify the individual. So Harvard came up with this idea called k-anonymity, where the idea is when I run an analysis, I should never be able to get more specific than 35 people. So if I wanted to figure out whether a certain individual had a disease, I might, in a normal system, I might be able to go in and type in his age. Even after he's been anonymized and masked, I might be able to go in and type in his age. I know kind of what hospital he would have gone to because it's the closest hospital to his house. And I put in, maybe I have racial information nowadays. I put in some information and I get specific. But k-anonymity says the moment you get more specific than 35, you don't get to see any further. The interesting thing about it is for statistical analysis, you actually don't care about a cluster whose size is less than 35 that much. So you are getting all the insights, all the statistical insights you could have wanted, but you're not revealing any of the privacy, any of the secrets. And again, we believe that as organizations start thinking about advanced analytics for all, if they don't bake privacy and security into the offering and make it a afterthought or make it something that you do through legal disclaimers, it's just never going to work. The next thing is how do you do the infrastructure? And I'm going to be very, very quick about this, the way we do it, but there are lots of approaches. We made the analysis server in Java, and we made the reports in pure HTML5. Now, why pure HTML5? Because that way you can have the report on an iPad, you can have it on an iPhone, you can have it on an Android device, you can have it on the cloud, you can have it on your web server, you can have it on your laptop, and it doesn't matter. It's the same code running everywhere, which really brings down the maintenance and organizational costs with these kind of technologies. Because if it's not simple to use, it's not going to be pervasively deployed, right? Those are the primary approaches towards advanced analytics for all. But let me show you a specific example and how we leverage these. So this is one of the leading hospital systems in the U.S., and they wanted to have us take a look at the patient length of stay patterns to figure out ways to improve the patient experience. And what we had to look at was 247,000 patient outcomes in this case. But if you look at the number of variables they had, to just look at third-order analysis, we actually had to evaluate 534,000 variable combinations to figure out what variable combinations were important. And you had to do about 9 million calculations to figure out what variable combinations were important because you want to do several statistical tests. You want to make sure the pattern you're showing is really statistically sound to the point made by the gentleman from Microsoft up front. If you just do a naive analysis and you don't do the statistical tests, you can be looking at a lot of confounding factors. You want to make sure that the pattern you're presenting is real. So we had to do about 9 million calculations. But after doing all of that, what the software did is it came out and said there are 35 key insights you need to look at. So it went from raw data to 35 key insights, and let me show you 3 of them, and I'm going to give you a quick slide on each of them after that. So the first one was the tracheostomy example I talked about, where people were 14.5 days longer in one hospital compared to the other. The second was kind of interesting, where we found that when a patient's diagnosis was altered mental state, people were staying 7.5 days longer in the surgical ward. And we went in and talked to the executives, and they figured it out actually fairly quickly. Because what happens is if the patient has altered mental state, the surgeon is often worried whether they'll get the follow-through treatment, right? And so what they're doing is they're keeping the patient in the surgical ward just to make sure that they're getting the right follow-through. But if this had been planned for, the moment you have a patient maybe with a psychiatric problem, if you had arranged to have the patient released to a psychiatric ward under appropriate care, you could have freed up the much more expensive surgical bed, which hospitals are always in short supply for, right? So that's an example of a pattern that once exposed to the client, people can quickly collaborate around it, and they kind of intuitively knew this was happening. They just didn't know the extent of the problem. So the extent of the problem becomes very clear, which allows people to rally around and act on it much more easily. The next one was a situation where, and remember, it controls for all possible variables, and one of the variables was the actual insurer. And what we found was for a certain treatment, people who had one insurance were staying 20 days longer than expected. Now, this is a pattern that is very, very intriguing, because on one hand, it might very well be that this insurance is an insurance that only people with really significantly bad diseases take, and so there is nothing surprising about the fact that people are staying longer. Or it might be it's a very high-end insurance that allows people to stay much longer. Or it could be a situation where an insurer is getting perhaps a little bit overbilled because they're paying by how many days a patient is staying in the hospital rather than based on the diagnosis, right? So if it's the latter, then hospital actually needs to figure it out and fix it before they get into potential embarrassing problems. Whereas if it's the earlier, it's just a false positive. It doesn't matter. But what happens today is if these patterns exist, if people staying longer exist, these patterns are going to be specific to specific hospitals for specific treatments. It's not going to be every hospital, every treatment that has that kind of overbilling situation. And administrators don't have the time to go look at every single diagnosis. So if they can quickly figure out where there are potential problems, they can quickly collaborate around it and figure out, is this a real problem? In that case, let's get ahead of the problem and let's fix it. And people tell me I'm naive, but I fundamentally believe that every one of these executives want to do the right thing. It's just that most of the time, they don't have the information at their fingertips to act on it. And most of the time, they can't quantify the extent of the problem, and they can't collaborate with their organization to figure out how to act on it. By simplifying what they look at and how to communicate with the rest of their organization, you can actually enable this kind of proactive collaboration. This is the example of the tracheostomy one I was talking about. If you saw this graph, by the way, those two call-outs are things I added, but otherwise that's exactly the screenshot you would see on your computer. And a human being can look at that and very quickly figure out, oh my God, I have a length of stay pattern that is intriguing. The next one I'm showing you is one of the insurance situations. So this is a specific diagnosis code, just like the last one was tracheostomy. And when I look at the diagnosis code, and by the way, these bars are sorted by how many of those diagnoses happened in that insurer. But as you can see, this one insurer has 10 days excess length of stay. And for this diagnosis, everybody has excess length of stay. So clearly this is a diagnosis where they're not doing so well in general. But for one insurer to have that significantly higher excess length of stay, that allowed the hospital organization to rally around figuring out what's going on there, right? So this length of stay patterns can be both useful from a treatment of patient perspective as well as what's going on with billing and coding perspective as well. Those were my primary slides, Julie, so if you have any questions for me.
Excellent, thank you. Yes, we do have several questions. So one of our audience members is wondering, what tools and language do you use to implement the statistics code?
We actually wrote our own statistics code using Java, so we actually are using some openly available Java class libraries, but essentially we wrote our own code because what we are doing, almost think of it like a search through all of the drivers of the outcome, right? It's a search-oriented approach to statistics as opposed to a traditional statistics-oriented approach to statistics, where you go systematically through every variable combination and calculate the statistics. That would just take too long if you have to calculate this much stuff. So because we had to come up with our own proprietary approach, it was just easy to write it in Java. But the approach I'm talking about, the broader advanced analytics for all, you could replicate this in any system that you want to do as long as you focus on how to focus on the examples rather than the statistics and how to make the analysis simple. You could do this in anything you want. The principle is more important than the specific implementation that BeyondCode Lucid built.
Mm-hmm. And you mentioned the issue of quality and maintainability of analytical code. But I, as well as one of our audience members, is wondering, sort of, when you have that wrapped under a visual solution, how can the analyst be sure that the software is giving the right results? In other words, don't you still need, 1 or 2 PhDs, or don't you still need specialists to make sure that the computer is doing its job?
Right. We call that showing our work. So it's actually kind of funny. We first came up with the executive dashboard that we expect people to use all the time, right? There you see 6 examples and in sort of tiles, visual tiles like the examples I was showing you, and you flip the tile and it shows you more detail for each example. But then we found that, hey, that was not detailed enough for the business analysts because they were like, I don't quite believe you. So we gave the business analyst the ability to go in and see exactly what variables were considered, how important of a predictive driver it was, etc. And you could drop down and see each example for each variable combination. And then we found the statisticians came in and said, well, what was R-square? What was RMS, right? I want to see a cluster graph. I want to see a topology graph. So we actually do put that in. So a statistician can go in and see a topology graph, can see a cluster graph, can see the regression, can see the root mean square. And that allows us, and we basically say that's just for winning debates with statisticians, right? So that the statistician can feel warm and fuzzy about these guys did some real work to come up with those 35 examples. But the power of the technology comes from being able to automatically figure out those 35 examples that are important rather than all the math we are doing to end up there.
Mm-hmm. So speaking of that number 35, that came up in the K-anonymity figure too, where it never gets more specific than 35 people. Why is that the magic number? How does it arrive there?
That was just this 35 was just an accident.
Sure. Yeah. Well, but the question still stands, and I'm sorry, but in addition, one of the audience members wonders if K-anonymity is not a hurdle against better results, and how do you balance that?
That's actually a very good point. So if you set the K-anonymity number very high, it would be a hurdle, right? Let's say I set the K-anonymity to 500. Then I might be losing some very important clusters. You can set K-anonymity as low as 10 if you want. I wouldn't recommend going lower than that because at the point of 10, you can probably start figuring out, you're down to 10 people, you might do some follow-on the ground research trying to figure that out, right? But the reason I like 35 is just as a statistician, I tend to not like clusters below 30 or 35 anyway. So I just said, okay, fine, you know what, I'm going to set the default to K-anonymity of 35 and let the users change it. Okay. On the other side, the examples we find, it might be 10 examples, it might be 100 examples. It just depends on what examples get above a certain threshold. And the user can always go in and say, show me more examples. So then instead of 35, they would have seen 70, or they would have seen 200, depending on how low we put the threshold above which an example becomes interesting.
Mm-hmm. Well, thank you so much, Arijit. And I hope that our next speaker will also address this issue of what is that ideal anonymity number. Our next speaker is Ann Waldo. She's a partner in the boutique law and public policy firm of Whitty, Lesh & Waldo, which is based in Washington, D.C. And she's going to come now and give us a reality check after some of this exciting potential that we've heard about personalized medicine. She'll talk to us about some of the privacy concerns and regulatory challenges that are standing, potentially in our way between where we are now and where we'd like to be. And then she'll make some suggestions for change. Ann?
Hello, everyone. Can you hear me okay?
We can hear you.
Okay, great. I'm pleased to be here with all of you today and eager to dive into such an interesting topic. The previous speakers have given us a great survey of the enormous potential in this area and the progress that's being made. And so I want to touch on some of the privacy and ethical risks and concerns that are being articulated not only today but as people try to look toward the future. I will, however, not dwell at great length on what's bullet number 1 there, the risks and concerns, because I think it's also important to look at specific practical obstacles as well as consider some suggestions for reducing the obstacles and bringing about positive change in order to accelerate research without compromising privacy. So that's where we're going to go with this in our limited time. I think one way to articulate the overall goal, there could be many here, but with respect to privacy and personalized medicine, an ideal setting would be in which individualized privacy needs and wishes are harmonized with appropriate use of genetic information. And I do think that's a very worthy aspiration, and there's a lot of exciting research being done in how to build out privacy solutions in more sophisticated ways. But I want to make sure that word appropriate is something we pay attention to. What is appropriate is certainly subject to disagreement. It's like the Supreme Court saying that I can't define it, but I know obscenity when I see it. We certainly wouldn't all agree on what the right balance is, but I hope we could agree that there is some appropriate balance of not only privacy safeguards but uses of genetic information and personalized medicine. Many privacy talks that you'll hear at conferences will focus entirely on privacy risks. The risk of re-identification, of breaches, of legal compliance, disasters, and costs, and so on. I just think it's important that we consider privacy risks in the context of looking at the risks of the status quo, because obviously the status quo has many failures in it. We have an enormously expensive healthcare system with poor outcomes in many cases, and there are countless diseases still untreated. So I am excited by the promise of personalized medicine, as I know many of you are, and I think it's crucial, just to get my own policy bias out there, that we build in privacy safeguards in really wise ways that also allow acceleration of science. Why else do we need to talk about privacy? The second point there is obviously because of legal compliance and risk mitigation efforts. This is a very complex area of law, as many of you know if you're in the research space, and understanding the privacy laws is crucial. And then there's yet another reason, which is that the more we increase public confidence about the security and confidentiality of one's information in any given setting, the more participation will be increased. And what I heard loud and clear from the other speakers is that greater numbers are certainly needed, and there's a lot of exciting work being done about how to increase the numbers of people participating in research and donating samples. Of course, it's important for us also to understand that some privacy risk is inherent in the storage and use and disclosure of such personalized data, and that we need to be very thoughtful and careful as we build in risk management and good controls. Again, I think what we're looking for is an ideal balance that continues to improve itself, much much like the learning healthcare system. We need a learning privacy system, but that the goal is not zero privacy risk. That's not a standard that we impose for driving cars or for taking medications or other interventions. We really do want to aim toward a situation where we protect privacy in a wise and cost-effective way while still accelerating science and progress. So diving in, laws aside, there are some factors that affect privacy that are completely independent of law. This will be obvious to many of you in the field. Obviously, very limited tests, such as genomic tests for a single condition, have less privacy risks than more comprehensive tests. Whether the test results alone are stored versus the genomic data being retained will obviously affect the risk, which is a real question for EHRs. Do just the results of 2 or 3 particular genetic tests go into my EHR, or will my genomic data actually be stored there? How and where the results and samples are stored, of course, matters. And so we just want to be aware of that as we're building controls. When you begin to look at the policy issues, you discover that there's a blurry line between privacy and ethics and patient autonomy, and at some point it doesn't make sense to particularly maintain those lines. As more and more can be learned about our bodies, some very interesting questions arise, and there isn't yet, I would say, expert consensus on the answers to these questions, let alone legal consensus. Science is certainly outpacing the law. But obviously a threshold question is, what should patients be told? Well, undoubtedly, they should be told the answers to the questions they have asked. And I say that with some emphasis because that isn't, even that isn't always the case in practice. I've seen that somewhere between 7 and 20% of lab results are never communicated to patients. So we obviously want to do a good job of answering the questions that are being asked. But the harder ethical question is what should be done when more information is revealed than what the question that was being posed in the first place. And again, that's very unclear. I think a lot depends on the clinical setting versus the research setting. Should what patients are told depend on whether an effective intervention exists? This is kind of a raging controversy in bioethics, and as it's cheaper to sequence the entire genome and learn more and more, it may be a considerable problem for a number of people if they're told information about the probability of certain events in their future that it may be very difficult for people to digest. I have an X% risk of this terrible disease and a Y% risk of that disease. And so that leads into the question of whether patients' preferences about what they want to be told need to be captured. And if so, how should you capture them, and can you thoughtfully do that in advance so that you're not struggling with a very difficult situation once new information is discovered. Another unsettled area in the law is what should be done if patients would like to have certain genetic information removed from their medical records. For an example, a patient with a BRCA gene wanted that information removed from her EHR. I guess she had decided not to do any particular treatment, and she was afraid of the information being passed around too freely and possibly being discriminated against. And of course, although the federal law GINA prohibits discrimination in medical insurance and in employment, it does not prohibit all forms of insurance. You can still be discriminated against, or in all forms of discrimination. You can be discriminated against with respect to life insurance and long-term care insurance, as some examples. And so she wanted that information out. However, since the information was accurate and it had been properly inputted by her physician, the current law really had no remedy for her. It's a tough question. I don't think there are easy answers about how we should handle information that is accurate but people might want to have removed or masked or not freely available. It's kind of a raging controversy in privacy circles in the healthcare space. And then the family members question is also a very troubling one. If a clinician or a researcher informs a patient about that they have a disease that has a very strong familial component, where does the professional's duty end? Do they have merely a duty to tell the patient and to urge them to tell their family members, or are they supposed to go further than that and tell the family members themselves? And if they do that, would that be a violation of the patient's privacy or autonomy? I was a little surprised at this question myself. I would have thought that it was merely the former, that when physicians start roaming into the land of telling family members, they may not even have a relationship with those family members, that would be getting down a very slippery slope and possibly invading patient privacy. But if I think that question hasn't arisen, I would be wrong, because in fact there's been litigation that's come out on both sides of this very question. In one case, a state Supreme Court concluded that telling the patient and urging them to tell their family did satisfy their duty. Although I'll tell you that still can't have been much fun for the physician, because the case went all the way to the state Supreme Court before the physician's decision was upheld. And then in another case, a state appellate court level, where the state Supreme Court declined to consider it, so it is the highest law of the land in that state, the court actually found that the physician must take reasonable steps to warn family members of a hereditary condition. So once again, there's no consensus among experts, and certainly not among lawyers and courts yet. Another tough issue, as many of you I'm sure know, is the question of recontacting patients. If someone donates their data or their tissue for research, what should be done if the researcher discovers something important? Well, clearly in many cases, people donate their tissue to an identifiable biorepository, and they want to be recontacted. So that makes it an easy question. But when it isn't clear up front, it becomes harder. There's a conflict between wanting to help the patient and a concern about invading their privacy, or perhaps a legal concern that it exceeds the scope of the original consent. And again, the bad news from the world of law is that there are legal risks for clinicians and researchers regardless of which decision they make in these cases. Both contacting and not contacting has gotten folks in trouble. I hate to be the bearer of bad news, but this is an area that certainly needs some clarity, and I would just urge someone designing a system to try to build that clarity in up front one way or another, so that people's expectations will be met. Sometimes researchers are so concerned about this recontacting question that they insist on working with fully anonymized data. And when we say fully anonymized, we mean that it's unlinked and unlinkable, cannot be traced back to an individual under any circumstances. And in some cases, researchers actually prefer that, even though the data may have lower utility, just because they know they lack resources to deal with any recontacting or deal with problems or legal issues. So the bottom line is that there just is not any consent yet. Any consensus yet. Furthermore, the consent issues become tough because I don't think consent solves all the problems. People's views on consent change over time, and they actually change in both directions. People become both more permissive about their consents, or put differently, less sensitive about their privacy, and more sensitive about their privacy, depending on their life circumstances and society evolving around them. Obviously, what can be done when the researcher wants to change the tasks that they're performing on the data over a period of time, and we'll get into that in a moment. And I also just wanted to point out that the law is not by any means the only thing you have to consider. There are numerous situations where an action by a researcher is clearly permissible under law. For example, when you're working with data that's been properly de-identified under HIPAA, but that doesn't necessarily end the question, because patients may want consent rights even where they don't have a consent right under law. And the prime example that I can think of for that is the litigation a couple years ago over a large set of de-identified newborn blood spots that were available for research use under an IRB in Texas, but litigation by a half a dozen parents resulted in a settlement with the state whereby, in my opinion, there was a tragic destruction of over 5 million unique blood spots, the largest blood spot collection in the United States. And so, we're in a world where just looking at the law isn't enough. You actually need to ponder what people want or want the law to be. Very tough decisions. So, having done that dipping of our toes into the tough and fascinating area of ethical questions, or you could go to entire conferences probing the matters that we just flew through. I want to do one quick bit of level setting on the types of data before we move into public policy. So with respect to research, there are really three types of data. The first is what is de-identified according to the HIPAA definition, which is a fairly strict and clear definition. There are two methods under HIPAA, the safe harbor method and the expert statistician method. Once data is de-identified per HIPAA, then it is no longer PHI, which is protected health information. That's also a term of art because once data is not PHI, it is no longer subject to HIPAA. It may be subject to state consumer protection laws, and that doesn't mean you have carte blanche to do whatever you please with it, but you don't have any requirements under HIPAA. Of the three types of data, it affords the greatest level of patient privacy, but of course that sometimes comes with limiting its utility. An advantage is that consent isn't necessary, and you escape a whole panoply of legal complex compliance requirements. Now, people have been saying for years and years that de-identified data lacks utility, but I can tell you that there's a lot of new research and some promising developments by computer scientists in this area, where I think the utility of de-identified data is growing where it's carefully done, and longitudinal matching between data sets, which is always a challenging problem, can be possible if they are carefully structured from the beginning. But there's going to be an entire session on that at Strata Rx. So small commercial, if you're interested in this de-identified question, would love to have you attend our session at Strata Rx. We're going to have one of the world's top de-identification experts on a panel. The next set is a limited data set, which does fall within the realm of PHI, meaning it's still subject to HIPAA. Most identifiers have been removed, but it has a greater utility than de-identified data, especially for population studies, because it allows two crucial fields that de-identified data does not allow, and those are full 5-digit zip codes and dates, meaning dates of treatment, dates of birth. And as Arjit pointed out earlier, those dates, along with other information, can pose a greater risk of re-identifiability, of course. So there is more of a privacy risk inherently in a limited data set than in de-identified data. But limited data sets are often absolutely crucial in order to match data sets that have been contributed across different institutions and pathways. The privacy risk of limited data sets was well understood when HIPAA was being written, and so the law requires the use of a data use agreement that would ban any attempt to re-identify the subjects or to recontact the subjects. And the limited data set tool is only available for research or for public health. You can't use limited data sets for say, commercial purposes, marketing and so on. So there are controls over that. The third category is the identifiable data, and this includes anything short of limited data sets. So it could be fully identifiable, or it could be what I call DID light or lightly pseudonymized, basic names removed, but more identifiers included. Obviously has the greatest data utility and allows recontact, allows retreatment if that's built into the program. it also requires consent, a full-blown HIPAA authorization for research in order for that identifiable data to be used, or an IRB waiver. But my friends in research tell me that IRB waivers are somewhat rare and challenging. So for all practical purposes, you should assume you're going to need consent for identifiable research, and that's a challenge. Blanket consent for future unspecified research is banned by HIPAA, and we're going to be talking further about that in a moment. That's a real challenge for researchers. So moving in now to the realm of public policy, and I'm going to shift to an editorial voice. And I will be expressing a perspective here, but I'll tell you that my point of view with regard to these matters really comes from the researchers that I've been talking to and reading, whose work I've been reading for years, more than any personal rant. I give personal rants in many areas, so I thought I'd make that distinction here. Personalized medicine clearly needs to remove data silos and barriers to data sharing. Everything you read about it says that. And such research is already facing challenges to the removal of those barriers. Some are proprietary and business-oriented, some are technological, some legal barriers and bureaucratic barriers. Many of you are no doubt already familiar with those and trying to come up with creative ways around them. I want to make sure, though, that this audience is aware of a new barrier to sharing data that was enacted in 2009 as part of the HITECH Act. The HITECH Act is a subset of the stimulus law of 2009 that created all of the financial incentives for electronic health records and a lot of other privacy provisions. This particular privacy provision is a ban on the sale of PHI, and as you'll recall from the previous slide, PHI is anything short of fully HIPAA de-identified data. This new provision seemed to be really aimed at marketing and commercial uses, but because it was written very broadly, it pulls research into its scope. The ban itself is very broad. It says that you can't, it's not just that you can't sell PHI, you can't have any direct or indirect remuneration. And when you think about complex contracts and business arrangements, you can readily imagine where many situations in which there would be indirect remuneration for the exchange of data that might be swept into the law. There is an exception for research, so that's the good news. However, the bad news is that the exception to the ban on the sale of PHI for research is quite narrow, and researchers don't think that the exception will get them where they need to go. The exception applies to an exchange of remuneration that only covers the cost of preparation and transmittal of the data. The problem is that there's several problems with that. One is that it's vague and highly subject to argument. It would be a challenge to get two lawyers or two CPAs to agree on what's the cost of preparation and transmittal, maybe even in the same organization, let alone in organizations that are sitting across the opposite sides of the table from each other, trying to negotiate a contract. Because it's vague, it's subject to a million arguments and potential litigation and regulatory compliance actions. Again, many of you know this better than I, but data transfers are not magic. They're not free. They generally involve contracts that have to be negotiated by expensive lawyers. They involve data work to purge data, to isolate the type of data that's involved, to dedupe it, to clean it, and so on. There's an actual transfer or mechanism that has to be built. There are data security controls. Sharing data is challenging under the best of circumstances, and I think it's frankly utterly unrealistic to think that data will be transferred I guess I should say to think that it will always be transferred without any corresponding financial payments. And then you go back to the scope of the exception, that there is an exception for the cost of preparation and transmittal. Well, even if we could all agree on what that means, it clearly refers to something related to the marginal cost of transferring the data. And I think even then, organizations will not be inclined to go to great lengths to make data available if their only compensation is their marginal cost. I mean, after all, every organization has its own agenda. Its IT department has its own remit for the year, and to go to significant lengths in order to transfer data and make it more liquid, when the most they can hope for is to be compensated for their marginal cost, not the cost of building the data set in the first place, and so on. It's just really unrealistic, and I think this provision is quite unfortunate, and it will end up diminishing data liquidity and thereby impeding research. You may be wondering why you haven't heard much about this, if I'm correct in surmising that you haven't heard much about it, and that's because while there was a lot written initially in 2009 when the law was enacted, first of all, it was an extremely comprehensive law. Even the privacy aspects of it were voluminous, and this one provision didn't get a lot of attention, particularly with respect to its effects on research. But in addition, this part of the law has not taken effect yet. It will take effect only after HHS issues final regulations, and they've been delayed for quite a long time, and attention has focused in other directions. But when the final regs come out, and I believe there's a 180-day period for it to take effect after the final regs, then expect to be hearing about this problem. Another obstacle that exists under the law today is the fact that HIPAA has from the very beginning banned what it calls compound authorizations, meaning that giving an authorization for the use and disclosure of your PHI can't be mixed together with an authorization for other things with some narrow exceptions. There is an exception that permits a patient to give their informed consent to a clinical trial and give consent for their PHI to be used in the trial, their HIPAA authorization. So that's somewhat helpful. But the big challenge is that today you have to have a separate consent for the donation of specimens, and increasingly, of course, that's a crucial part. And for personalized medicine, it's absolutely essential that tissue and blood samples be collected and be available for analysis. The separate consent requirement causes increased confusion and complexity, and sometimes just consent exhaustion when a person is going through a lengthy informed consent procedure and they get down to the last piece of it, asking for consent to donate their samples. They may just be inclined to say no because the process has been challenging, and so I'll give HHS praise on this point. I should have put this in the slide here. HHS recognized this problem. The research community has been complaining about it for a decade, and so in the proposed high-tech rule, they propose to go to at least take some very nice steps in the right direction towards solving this problem and allowing a consent for trial participation and for data use and for donation of specimens all in one document. The problem is that is still pending until the final HIPAA regs are released, but at least we're moving in the right direction in that regard. There's some technical aspects to this where I think they could have gone a little bit further and made it even simpler yet, but at least there can now be one document. Yet another problem has to do with the consent to future unspecified research. That has been banned by HIPAA from the beginning, and it creates a disconnect between HIPAA and the common rule that applies to federally funded research. The common rule allows participants to consent to the use of their information in future research as long as the future research is described in sufficient detail to make the consent informed. But however, HIPAA does not do that. So that's yet another problem. It creates a really burdensome process and actually prevents altruistic patients from being able to donate their data and samples freely to benefit others, which is something that we see often when people have critical illnesses, terminal illnesses. Their real choice is to donate their data and their samples freely without any conditions. And the law, again, in my opinion, is pretty paternalistic here and says, no, we won't allow you to consent in that broad manner to future unspecified research, which is a real burden for those who are coming up with important new questions in the future. So where do we go from here? I have a number of concrete suggestions for improvement, and given more time, we could come up with a lot more. This is really just a starting point, but I think these are important ones to consider. First of all, if I would certainly love to see that research be exempted entirely from the current ban on the sale of PHI. There are other proposals that have been under discussion in the comments that were written to the proposed high-tech rule, some fallback positions where you tinker with the cost caps, you broaden them, and so on. But I really think any form of cost cap on compensation that can be exchanged for data movements in research will just continue to add complexity and legal uncertainty and legal fees and serve to inhibit research. So I think that exempting research entirely would certainly be the best thing. The bad news is that probably would take congressional action. It's highly unlikely that HHS would or probably even could go that far on their own, given the language in the law. But that's something to ponder if you folks are interested in advocacy of just seeking a change to get research entirely out of that ban. If I were czar and doing that, I would also, on the second point, extend that logic to exempt related types of studies. There's often a very blurry line between what is research and what is a quality study, a safety and efficiency study, and so on, rather than fight and spend massive legal fees on where that line is drawn. I think it would be best for society, best for patients to exempt those types of studies from this ban as well. Number three is really a fallback position. If we were to get one and two, we wouldn't need number three. But if Congress and HHS policymakers really won't go so far as to exempt research, then I think we certainly should be exempting limited data sets from the ban on sale of PHI, because they are already subject to quite a number of contractual protections. And there's really been somewhere between little and no evidence that there have been violations in that regard. I'm aware of no evidence, but I hesitate to say that there actually is no evidence. But there certainly are strong both ethical and legal requirements applicable to limited data sets. Point number four that I would like to see is the one that the administration would also like to see, which is to permit compound patient authorizations in research. That's very important in order to reduce bureaucracy and reduce the overall cost of enrolling patients in clinical trials. Number five is a tweak actually on number four. This starts to get more technical, but the proposed rule does allow compound authorizations for specimen donation in trials, but it still says that there has to be an opt-in for any research, any aspect of the study that is conditional, or that is not required. So as best I understand that, if you don't require the submission of specimens for your clinical trial, then you need to have an opt-in. And I have heard from researchers and those who run biorepositories that that's not a good idea, because people actually get confused. Again, they they get consent exhaustion, legal document exhaustion, and there are cases where patients have actually gone to the trouble to prepare their specimens and their DNA samples and send them in to biorepositories, but because they fail to check an opt-in box, the specimens can't be used, and the patient has to be recontacted and asked to recheck the box. Obviously, their intent was to have their specimens used because they went to the trouble to collect them and send them in. So I think that we could address this problem through a consumer protection standard of really clear and conspicuous language so that people know what they're doing. I would also like to see number 6 that we allow consent for future unspecified research. Again, provided it's clear that that's what people are consenting to, I think people should be allowed to consent to whatever they want, and that's very important for science. And then 7 is a broader recommendation that in various places throughout the law we allow for simpler consent processes rather than continually making them more and more heavy laden. There's a strong altruistic streak today, and I think that should be encouraged. I think I'd like to see people being offered opportunities to participate in research, to offer their data for research, to offer their samples, and have those consent opportunities be simple, so that we start to see consent being easy and convenient and common rather than the opposite of those. So I will stop there. I know I've presented a ton of information and would love to take questions.
Thank you, Anne, so much. Yeah, that's a lot of really important information and a great survey. Thank you. We have a couple of questions. Hagen is wondering if there are any examples of genetic and personalized medicine patient data having been compromised, and if so, has there been material personal injury from that?
That is a very interesting question. Obviously, if you follow the privacy press or even the popular press at all, you know that data breaches in healthcare are extremely commonplace. We're seeing them almost daily. As an overall statement, I think it's fair to say that the healthcare industry is growing in its. I mean, there's no question that it's growing dramatically in terms of imposing better and better safeguards, but that it still has a long way to go. A lot of that is human error and inevitable error. So are there breaches where patient data in general gets exposed? Of course there are. Laptops get stolen and lost, and institutions haven't yet gone to the expense of encrypting the data. That happens every day. But to your more precise question about genetic patient data being compromised and material personal injury, those aren't the kind of news stories that we read about. I certainly can't say it hasn't occurred, but that's really not. It's far from common. I can say that with assurance, and I'm not aware of any particular examples of it at all, unless if you did some research, you might find an individual case that. But I'm not aware of any large scale breaches of that nature. When it comes to de-identified data, there's been a lot in the press. This is actually the subject of a much bigger question, of what are the risks of de-identified data being re-identified. Whole conferences are held on that topic. A lot has been written. I frankly think that the risks of re-identifying de-identified data have been seriously exaggerated in the popular press and in the legal press. Authors often fail to make a distinction between HIPAA de-identified data, which has been subject to a very high bar laid out in statute and built out over 10 years of computer science, versus consumer data that has been, quote, anonymized, but in a completely standardless environment where literally I as a non-statistician might, take names and addresses off of a data set, make it public, and call it anonymous, and some of those types of data sets have been successfully re-identified through computer science attacks. I will say, though, that those have been mostly done, or maybe even entirely done in the reported cases, by academic computer scientists who are trying to do research in the whole field of how easy re-identification is or is not. So to your question, really we have not seen significant numbers, if any numbers, of material injury from genetic data being compromised. And having said that, I'm sure someone can be doing Google searches and we'll find a case or two I'm not aware of, but it's not a large phenomenon. Other questions?
Forgive me, I was on mute there. Dave is wondering if the sale of PHI should be tracked.
Are you talking about with respect to research or in general?
He doesn't specify. Do you have an opinion on either?
Okay. Well, I would, with respect to research, I would say no, pretty resoundingly. I can't see any value in that, and I see enormous cost and inhibition, further inhibition of research. It's sale of PHI for other purposes and tracking it. It's an interesting question. I think it's probably mooted by the current law because the law now bans the sale of PHI with very narrow exceptions, and unless you have specific patient authorization, which again is going to be quite rare. It's going to be very rare that a patient will ever be even asked to, let alone willing to, consent to the sale of their PHI as opposed to their consumer health information that's in their own hands, but their PHI from a HIPAA-regulated healthcare institution. It's really pretty unthinkable that one of those institutions would be asking for permission to sell it for marketing purposes, and if they did, they'd have to follow very strict guidelines in the law. And I guess if all of those contrary to fact events happened, I wouldn't see any advantage in tracking it. But again, that's my opinion.
Yeah. Finally, Jeremy is attempting to sort of encapsulate everything that you've said in the following way, and he's wondering if you would agree with this, that perhaps no sharing of patient health data where the patient can be identified without a specific and time-limited authorization from the patient for that sharing might be a good idea. Does that make sense as a basic principle?
No sharing of identifiable data without a specific and time-limited
authorization from the patient, right?
Yeah, I do think some people resonate with that point of view. My own perspective is actually to the contrary. I think that that's really where I guess I was going with my suggestion number 6. I think that if a patient is motivated enough to help their children and grandchildren and countless people they'll never know to donate their data and their specimens for unspecified research, not time limited, not specific, then I personally would be strongly in favor of that. I've done a lot of work for a patient advocacy group, and it's really from those folks that I developed this opinion that many people who have terrible diseases, and in particular rare genetic diseases, are toward the end of their lives, they want more than anything for a cure to be found to help other people. And so if they want to donate their samples and data to be used for all time for any purpose to benefit medical research, I'd be in favor of allowing them to do that.
Well, thank you very much, Anne. Thank you to all of our speakers, and special thanks to all of you there in the audience for joining us. As Anne pointed out, this is sort of the tip of the iceberg. Each of these presentations has been the tip of a separate iceberg of a conversation that we will continue at Strata Rx, which is happening in San Francisco on October 16th and 17th. You can register for that conference or see the lineup of speakers if you go to strataconf.com/RX2012. We'll also be live streaming the keynotes from that event, so check the website for the live stream link once the conference begins if you're not able to actually be there. Also, as Yasmina let us know at the beginning of this broadcast, we've been recording this online conference, and that will be available soon. Yasmina will let us know more details about that, but you'll be able to go back if you had to step away for a few minutes, or if you have a colleague that you'd like to share this presentation with, feel free to do that. We'll also be posting slides from the speakers. I know that both Michael Simpson and Ann Waldo had some additional slides that we did not have time to get to, so if you would like to learn more about TraitWise or about the privacy issues of personalized medicine, you can check back both to review and to learn some more. So again, thank you to all of our speakers. Thank you to Yasmina, and thanks to all of you for joining us.
Great. On behalf of O'Reilly Media, folks, we thank you all for attending today and hope you benefited from the event. We did push out the group chat for you all, so please, if you haven't opened the group chat, do open it. There's some codes in there to save you some money on the conference registration, as well as a code to save you some money on books and videos as a thank you for attending. We have recorded the event. It will be available within the next 48 hours, so we will email you all access to the archive. Thank you to all our speakers. Thank you, Julie, for organizing the event. Thank you, attendees. Goodbye, everybody.